Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the electronics engineering. Today we are moving to the next section where we will be talking about the various applications of the semiconductor diode. I hope all of you know what is a semiconductor diode. I had already talked about it in the previous videos as well. If you have still any kind of doubt, you can go and watch the previous videos. Now we will be talking about the various applications like the rectification. The rectification is required because most of our appliances we are using the DC current, right? Then we will be talking about the various other applications like the clipper, clamper, and the voltage regulator of the diode, right? So these applications are really important and we are going to have an in-depth analysis about all of them, and at last we will be talking about some numericals as well, like we do, right? So let's start our discussion, but before talking about the application we should understand what happens when I connect the diodes in series and parallel. So today we are going to talk about the series connected diodes, right? So now I have two diodes which are connected in series. Now when I connect two diodes in the series, it is also known as side by side configuration, right? So both of the diodes are connected side by side and there is one important phenomena that they have only one common junction, right? So if we have one common junction, then the series connection would be there, right? So now we would be having some variation in the voltage and the current in the series configuration, right? Previously, if I was using a single diode, I was having some voltage and current. I already saw the various equation for the voltage and current when I have a single diode. Now what would happen to the voltage and current when I have two diodes which are connected in series? Potential difference across every component would be different. We all know when I have a series connection, the current in the series connection would be same, so current will be moving through both of the diodes would be same, but the potential difference that is existing on both of the diodes would be different. So potential difference across every component is different, and the series connection, the current across every component remains same, right? So this is a property of the series connection that we all know. Now what is the diode characteristic when we have the series configuration? So the resultant diode's forward voltage becomes high. We will be operating at a higher forward voltage and the reverse blocking capability of diode will increase when they are in series connection. So you can see here we have a circuit. Now this is my diode 1 and this is my diode 2. We are supplying some voltage over here which is represented by Vs. Now current Is is flowing through both of the diodes, so I will be having the same current flowing through both of these diodes, and the voltage across these two diodes would be different, which is represented by V01 and V02, right? I hope you understood what is the series configuration. Now coming to the Vi characteristics. Now when I see the forward characteristics, I will be having the same voltage, right? But if I talk about the reverse characteristics, both of the diodes will be having the different voltages, right? So in the reverse characteristics, diode have different blocking voltages. You can see from this graph that now this white graph will be having the voltage, that is blocking voltage, as V02, and the yellow dotted graph will be having the blocking voltage V01. So both of these graphs are having the different blocking voltage. Now when I have the forward bias, voltage drop and the forward current will be same, right? But in the reverse bias we have seen the voltage drop is different but the current is same, right? So you can see current, the leakage current is represented by Is over here, which is same. Now in the reverse bias we have different blocking voltage as diodes have to carry the same leakage current, right? So you can see at the same leakage current we have the different voltage, right? So now how this problem is overcome? This problem is overcome by connection of the two resistance, right? So if I connect the two resistance across the diodes, the voltage is shared equally and the leakage current would differ, right? So you can see when I connect the resistances R1 and R2 across the diode D1 and D2. So here I have connected R1, here I have connected R2. This is my diode D1, this is my diode D2. So now at this time the leakage current would differ, but the voltage across the diodes will become equal, and this is how our characteristic would change. Now here we will be having the reverse voltage to be equal to minus D1 is equal to minus D2, but the reverse leakage current would be different, right? So I hope you understood how we have the difference in the reverse leakage current and the same voltage, right? So with the help of this type of circuit I can have overcome the problem, right? So now understanding the leakage current, how we can denote the leakage current from this circuit. So you can see over here, if I characterize IS over here, so what would be the IS? You can see IS is given by IS1 plus IR1 and IS2 plus IR2, right? So you can see IS is splitting into IS1 and IR1, right? And IS is also splitting into IS2 and IR2. So IS will be equal to IS1 plus IR1, right? So this is the Kirchhoff's current law that we all know, right? So with the help of Kirchhoff's current law, I can say IS is equal to IS1 plus IR1 is equal to IS2 plus IR2. And now at this moment I already know the voltages across the diode are same. VD1 is equal to VD2. So how I compute the IR1? You can see IR1 over here, the current which is flowing through this resistor will be equal to now VD1. This is the VD1, the voltage across here, because the diode and the resistors are connected in parallel. So the voltage across the diode will be the voltage across the resistor, right? So here at the resistor we will be having VD1 voltage, and if I divide it by R1 I will be getting IR1. Similarly, how I get IR2? VD2 upon R2. So I hope you understood how I wrote these two equations. IR1 is equal to VD1 upon R1, IR2 is equal to VD2 upon R2. So now replacing the value of IR1 and IR2 over here, so IS1 plus VD1 upon R1 will be equal to IS2 plus VD2 upon R2. Now we know both of the diode voltages are same. I can say VD1 is equal to VD2. So when you put VD instead of VD1 and VD2, so you can see IS1 minus IS2 will be equal to VD 1 upon R2 minus 1 upon R1. So this is how I can calculate the difference between the reverse leakage currents, right? So these are the difference between the leakage current. In the reverse direction we have the leakage current, and this is the diode voltage, and these are the two resistances that we have connected across the two diodes. So I hope you understood how we calculated the leakage current, right? So now coming to the applications of the series configuration. What are the applications? So it will be used when we cannot meet the high voltage requirement, right? It can be used in the high voltage direct current, because if I use a single diode there, it will not be giving me high voltage. So it will be used in high voltage direct current transmission line, HVDC transmission line, and after that it is used in the commercial areas where regulated voltage supply is required, right? So with the help of the regulation of the voltage in the reverse bias as well, we can have the regulated voltage in the commercial uses as well. I hope you understood all of the things related to the series configuration. If you have any doubt, you can put the doubt in the comment, and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.